Yes, a three-phase power bus system with neutral and ground is a common power distribution system in the United States. It is typically used for commercial and industrial applications that require a reliable and efficient power supply. In a three-phase power system, the neutral wire does not typically carry significant current under balanced conditions. However, it can carry current during unbalanced conditions, such as when one phase is overloaded or there is a fault. For derating purposes, the National Electrical Code, or NEC, requires a neutral wire to be considered a current-carrying conductor. This is because the neutral wire can experience overcurrent conditions during unbalanced loads or fault conditions. When sizing wires for a three-phase power bus system with neutral and ground, it is important to consider firstly the load current requirements of the equipment, secondly the unbalanced load conditions that may occur, thirdly the NEC requirements for wire sizing and derating, and fourthly the applicable electrical codes and standards. It is always advisable to consult with a qualified electrician or electrical engineer to ensure that the wire sizes are properly selected and installed. Let's delve deeper into the aspects mentioned. A three-phase, four-wire system comprising three-phase conductors, a neutral conductor, and a ground conductor is indeed a standard configuration for power distribution in many industrial and commercial settings across the United States. The primary advantage of this system lies in its ability to provide both three-phase power for heavy-duty equipment and single-phase power for lighting and other general-purpose loads. Each component of this system plays a crucial role in ensuring safe and efficient power delivery. The three-phase conductors, typically labeled A, B, and C, carry alternating current that is offset by 120 electrical degrees. This phase difference allows for a more constant power delivery compared to a single-phase system, reducing the pulsations in power that can affect the performance of motors and other sensitive equipment. The neutral conductor serves as the return path for current in a single-phase circuit and helps to balance the load in a three-phase system. Under ideal conditions, where the loads on each phase are perfectly balanced, the neutral conductor would carry minimal current. However, in real-world scenarios, loads are rarely perfectly balanced, and the neutral conductor plays a vital role in carrying the imbalanced current, preventing voltage imbalances across the phases. The ground conductor, also known as the equipment grounding conductor, is a safety feature designed to provide a low-impedance path for fault currents back to the source. This ensures that in the event of an insulation failure or short circuit, the fault current will quickly trip a circuit breaker or fuse, minimizing the risk of electrical shock and fire. Now, let's discuss the conditions under which the neutral conductor carries current and the implications for derating. In a balanced three-phase system, the currents in each phase are equal in magnitude and 120 degrees apart. The vector sum of these currents ideally cancels out at the neutral point, resulting in zero current flowing in the neutral conductor. However, several factors can lead to imbalanced conditions and cause current to flow in the neutral conductor. These factors include unequal loading on the phases, single-phase loads connected between a phase and neutral, and harmonic currents generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonic currents, especially the third harmonic and its multiples, are particularly problematic because they are additive in the neutral conductor. Unlike the fundamental frequency currents, which tend to cancel each other out, the third harmonic currents from each phase are in phase with each other in the neutral, leading to a significant increase in neutral current. For derating purposes, the NEC requires that the neutral conductor be considered a current-carrying conductor under certain conditions. Specifically, if the major portion of the load consists of nonlinear loads, the neutral conductor must be counted as a current-carrying conductor when determining the ampacity of the conductors. This is because the harmonic currents can cause the neutral conductor to overheat, potentially leading to insulation damage and fire hazards. The NEC provides specific guidelines for derating conductors based on the number of current-carrying conductors in a raceway or cable. The more conductors that are carrying current, the more heat is generated, and the lower the ampacity of each conductor must be to prevent overheating. The derating factors are specified in NEC Table 310.15 cone. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its rated value. When sizing the conductors for a three-phase power bus system, several factors must be taken into account to ensure that the system can safely and reliably carry the intended load. These factors include the load current requirements of the equipment, the anticipated unbalanced load conditions, the NEC requirements for wire sizing and derating, and the applicable electrical codes and standards. The load current requirements of the equipment can be determined from the equipment nameplates or manufacturer specifications. It is important to consider both the continuous load and any intermittent or surge loads that may occur. The unbalanced load conditions can be estimated based on the expected usage patterns of the equipment. If the loads are expected to be relatively balanced, the neutral conductor may not need to be sized as large as the phase conductors. However, if the loads are expected to be significantly unbalanced, the neutral conductor should be sized to carry the maximum anticipated neutral current. The NEC provides specific guidelines for wire sizing and derating in Article 310. These guidelines take into account the ampacity of the conductors, the ambient temperature, the number of current-carrying conductors in a raceway, and other factors. The applicable electrical codes and standards vary depending on the location of the installation. It is important to consult with a qualified electrician or electrical engineer to ensure that the installation complies with all applicable codes and standards. To summarize, designing a three-phase power system requires careful consideration of several factors to ensure safety, reliability, and compliance with applicable codes and standards. These factors include understanding the role of the neutral conductor, recognizing the potential for unbalanced loads and harmonic currents, applying the appropriate derating factors, and selecting the correct wire sizes. Consulting with a qualified professional is always recommended to ensure that the system is properly designed and installed. It is crucial to understand the role and behavior of the neutral conductor in a three-phase system to ensure the safe and efficient operation of electrical distribution networks. The neutral conductor in a three-phase, four-wire system serves as the return path for current, particularly in single-phase loads that are connected between one of the phase conductors and the neutral. The primary purpose of the neutral is to maintain a stable voltage level across all phases, especially when the loads are not perfectly balanced. In an ideal scenario, where the loads on each phase are perfectly balanced, the neutral conductor would carry little to no current. However, real-world electrical systems rarely achieve perfect balance due to variations in load types, usage patterns, and equipment characteristics. As a result, the neutral conductor often carries a significant amount of current, which can have important implications for system design and safety. One of the key challenges in managing neutral current is the presence of harmonic currents. Harmonic currents are multiples of the fundamental frequency of the power system, which is typically 60 Hz in the United States. These harmonics are generated by nonlinear loads such as electronic devices, variable frequency drives, and energy-efficient lighting systems. Unlike the fundamental frequency currents, which tend to cancel each other out in the neutral conductor, certain harmonic currents, particularly the third harmonic and its multiples, are additive. This means that the third harmonic currents from each phase combine in the neutral conductor, potentially leading to a neutral current that is significantly higher than the current in any of the individual phase conductors. The presence of excessive harmonic currents in the neutral conductor can cause several problems. Firstly, it can lead to overheating of the neutral conductor, which can damage the insulation and increase the risk of electrical fires. Secondly, it can cause voltage distortion and interference with sensitive electronic equipment. Thirdly, it can reduce the overall efficiency of the power system and increase energy losses. To mitigate the risks associated with neutral current, several strategies can be employed. Firstly, it is important to balance the loads as much as possible. This involves distributing the single-phase loads evenly across the three phases to minimize the imbalance current flowing in the neutral conductor. Secondly, harmonic filters can be used to reduce the levels of harmonic currents generated by nonlinear loads. These filters typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. Thirdly, oversized neutral conductors can be used to accommodate the increased current carrying capacity required by harmonic currents. The NEC provides specific guidelines for sizing neutral conductors in three-phase systems. In general, the neutral conductor must be sized to carry the maximum unbalanced load current. However, if the major portion of the load consists of nonlinear loads, the neutral conductor must be sized to carry at least 100% of the phase conductor ampacity. In addition to sizing the neutral conductor appropriately, it is also important to ensure that the neutral conductor is properly grounded. The neutral conductor should be grounded at the service entrance and at other points throughout the distribution system to provide a low impedance path for fault currents. Proper grounding helps to minimize the risk of electrical shock and equipment damage. In conclusion, the neutral conductor plays a critical role in the safe and efficient operation of three-phase power systems. Understanding the behavior of neutral current, particularly the impact of harmonic currents, is essential for designing and maintaining reliable electrical distribution networks. By implementing appropriate strategies for load balancing, harmonic filtering, and conductor sizing, it is possible to mitigate the risks associated with neutral current and ensure the long-term performance of electrical systems. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment in the United States. It is developed and published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. The NEC is not law itself, but it is widely adopted by state and local jurisdictions as the basis for their electrical codes. Compliance with the NEC is essential for ensuring the safety of people and property from electrical hazards. The NEC covers a wide range of topics related to electrical installations, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for conductor sizing, raceway fill, and derating factors, as well as specific rules for different types of equipment and applications. One of the key principles of the NEC is to provide protection against overcurrents. Overcurrents can result from short circuits, ground faults, or overloads, and can cause overheating, insulation damage, and electrical fires. The NEC requires that all electrical circuits be protected by overcurrent devices, such as circuit breakers or fuses, that are sized to protect the conductors and equipment connected to the circuit. The NEC also places a strong emphasis on grounding. Grounding is the process of connecting electrical equipment and systems to the earth to provide a low impedance path for fault currents. Proper grounding helps to minimize the risk of electrical shock and equipment damage. The NEC provides detailed requirements for grounding electrode systems, grounding conductors, and equipment grounding conductors. Another important aspect of the NEC is its focus on safety. The NEC includes numerous provisions designed to protect people from electrical hazards such as shock, electrocution, and arc flash. These provisions include requirements for ground fault circuit interrupters, or GFCIs, arc fault circuit interrupters, RF size, and personal protective equipment, or PPE. The NEC also addresses the installation of electrical equipment in special occupancies, such as hazardous locations, healthcare facilities, and swimming pools. These occupancies require special precautions to minimize the risk of electrical hazards. The NEC is a complex and comprehensive document, and it can be challenging to navigate and interpret. For this reason, it is always advisable to consult with a qualified electrician or electrical engineer when designing or installing electrical systems. These professionals have the knowledge and experience necessary to ensure that the installation complies with all applicable NEC requirements. In addition to the NEC, there are other electrical codes and standards that may apply to a particular installation. These include state and local electrical codes, as well as standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. It is important to be aware of all applicable codes and standards and to ensure that the installation complies with all requirements. In conclusion, the NEC is a critical resource for ensuring the safe installation of electrical wiring and equipment. Compliance with the NEC is essential for protecting people and property from electrical hazards. Consulting with a qualified professional is always recommended to ensure that the installation meets all applicable requirements.